Welcome back, everyone, to the afternoon session of day 2 of ISARC. This afternoon, we will be focusing on ways to design the 5G radio layer for resilient services. We will start with a technical talk on O-RAN and then move to our panel of experts from government, industry, and academia. A reminder, at the end of the panel, we will then move to breakout rooms where you will have the opportunity to interact one-on-one with not only the panelists, but also our technical. Our technical presentation today will offer a deep dive into the current state of Open Radio Access Networks, known as O-RAN. Please remember that you can submit questions during this presentation in the Q&A button on your right. This technical presentation will offer a deep dive into the current state, and it is my pleasure to introduce Mr. Brian Daly, the Assistant Vice President for Standards and Industry Alliances for AT&T, where he oversees AT&T's strategy and leadership in global industry standards. His focus includes, among other things, emerging technologies for 5G and beyond, public safety initiatives including FirstNet and wireless emergency alerts, and IoT including smart cities and UAVs, and of course cybersecurity. Mr. Daly is extremely active in guiding wireless development around the world. His many, many roles include board of directors on the IEEE ISTO. He's co-chair on the FCC's Technological Advisory Council 5G IoT Working Group, and also the co-chair of the O-RAN Alliance Standards Development Focus Group, and several other key industry organizations. There is much more I could say about him, but I will encourage you to use the app and our program to peruse his complete bio information, where you can learn much more about him. And now I will turn this over to our speaker, Mr. Brian Daly.
Thank you, Melissa. I appreciate the introduction, and we'll start with the slides. So if we move to slide 2, we'll jump right into the Open Radio Access Networks. So first off, why Open RAN? As most of you are probably aware, the goal of having open interfaces is to avoid a lock-in effect where we have proprietary or semi-proprietary implementations, especially in the radio access network, which tends to inhibit competition among suppliers. When we look to the future, we want to see RAN, the radio access network, built on a foundation of virtualized network elements, white box hardware, and standardized interfaces that really embrace what we're trying to do with intelligence and openness at the radio access network. This will allow operators to have a mix of equipment from different suppliers in the same RAN, something that's challenged today, and also allows us to bring other layers of the network into the RAN, for example, the operations and maintenance layer, and provide a common OANM platform for both the core and RAN network elements. Next slide, please. So one of the things I would like to make sure we're clear on is some of the terminology. When we hear Open RAN, O-RAN, and so forth, they mean slightly different things. So Open RAN itself is the general idea of disaggregating the RAN functionality using open interface specifications between the elements. This is what we think of when we talk about Open RAN. When we use the term O-RAN, typically that means the O-RAN Alliance, or the specifications that are being developed by the O-RAN Alliance. This is a group that's defining the next generation RAN infrastructures, and really is looking at those intelligence and openness principles that I mentioned earlier. But they're not the only group looking at opening up the RAN. There is also the Telecom Infrastructure Project, or Telecom Infra Project, which is another community that has more than 500 network operators and telecom companies, etc., that are also developing open and interoperable interfaces and technologies. And then finally, there's vRAN, or virtualized RAN, which is implementing the RAN in a more open and flexible architecture that allows the virtualization of the network functions into software platforms. So that really tries to summarize the different terminologies that we use when we talk about openness in the RAN, as well as highlighting some of the groups that are involved within the Open RAN development. If we move to slide 4, please. So when we look at Open RAN standards, 3GPP, I'm sure everybody's familiar with, is the third generation partnership project, which are really developing the global 5G specifications. However, the openness of the interfaces between elements within the RAN or core network, that's really the key to disaggregating the RAN and allowing additional suppliers to enter the market. So the O-RAN Alliance and TIP are developing specifications that go beyond what 3GPP is developing within the RAN itself to allow this disaggregation of those elements. And these are complementary to standards promoted by 3GPP. It's not, a competition between standards. It's really taking 3GPP standards, taking the RAN that's being defined by 3GPP and advancing it such that you can disaggregate it into further functions that allow this virtualization and softwareization. The O-RAN Alliance, as I mentioned, has developed specific specifications for this, and the TIP project also are looking at that. If we move to slide 5, please. There is also the O-RAN software community, which is a collaboration between the O-RAN Alliance and the Linux Foundation. And this has the mission of actually creating the software for the radio access network in the open source community. It's leveraging other Linux Foundation projects and addressing challenges in performance, scale, and 3GPP alignment. There's an initial set of projects being discussed, including the intelligent controller, and we'll talk a little bit more about the architecture on the next slide, cloudification and virtualization platforms with an open central unit, an open distributed unit, as well as test and integration efforts so that we can provide a reference implementation. Next slide, please. This is the O-RAN Alliance architecture. We're not going to be able to get it into too many details on today's session because it does require quite a bit of effort to go through and define each one of these. But it's sufficient for this effort just to say that this architecture is based on well-defined standardized interfaces. And what we want to do is have an open interoperable supply chain ecosystem that's supported by and complementary to 3GPP and other industry standards organizations. And again, the goal is to use commercial off-the-shelf hardware with virtualization software that enables abstraction in the form of virtual machines or containers to provide multiple hierarchical cloud development options. Next slide, please. As we look a little bit deeper into the logical architecture, we recall that the RAN was typically traditionally built using specialized, expensive devices, had a small number of vendors, which really dictated everything about the RAN, from cost to capabilities to upgrade schedules and so forth. And when we move forward, with 5G and beyond, that type of model really doesn't make much sense anymore. So what we want is to create open hardware specs that any manufacturer can build to, use the software running on those devices from an open source community, an open source library, empowered by the principles of intelligence and openness, and make the architecture the foundation for building virtualized RAN on open hardware with embedded AI-powered radio controls. So we want to bring that intelligence in, have it software-defined, AI-enabled RAN intelligent controller, which really gives the heart of this O-RAN logical architecture being that 5G RAN intelligent controller, or RIC, as it's known. If we move to slide 8, please. So let's talk a little bit about security when we move to an open RAN architecture. Now, when we have this architecture, we do have a more modular design. We're going to have different suppliers providing different components in the network, and actually that can enhance security because it will allow operators to more quickly replace or address network problems, including suspect equipment. A more intelligent RAN also will enable operators to deploy the security capabilities closer to the network edge. As we move the intelligence into the RAN, as we move the RAN into a more distributed and software-defined, we're able to deploy security capabilities out to the edge of the network, and that'll allow us to more quickly respond to threats and shift network capacity on demand. Now, an Open RAN also provides the framework for all stakeholders to align on a shared understanding of the security requirements so that we can tailor those requirements at a more granular level that has been possible before. Since we have a more modular design, since we're virtualizing the elements and components on the network and providing a focus on the security requirements, we have the ability to tailor those requirements at that more granular level that we're doing. A RAN based on open standards also helps both the users as well as network operators better understand, align on, and demonstrate successful implementation of security requirements. And the other thing to keep in mind is in the software development, we need to introduce secure software development practices into the software community. And that could be through vulnerable library upgrade practices, software composition analysis, security tests, and so forth. We want to treat the ORAN as a zero trust environment, and ORAN security would be defined following best practices such as those in the NIST zero trust architecture. Performing a risk analysis on both the C and S plane traffic to determine if the risk justifies the cost of adding encryption to the front haul interface, and also investigate security use cases that will be core to ORAN, and one that comes to mind, especially when you move to an massive IoT environment, is signaling storm detection and mitigation. If we can move to slide 9, please. So what has the ORAN Alliance been doing? They've been doing a lot of work. They've published 23 new or updated specifications recently. There's a new white paper that came out earlier this year on use cases and development scenarios, which is available on their website. And they also have been looking at a cloud computing platform that can host relevant ORAN functions to enable flexible deployment options in virtualized telco clouds. Recently, they had the second release of the ORAN software called Bronze, and this provides some new key elements of the ORAN architecture and updates the alignment with the latest ORAN specifications. So in here, we have the initial release of the A1 Interface Policy Manager and an A1 controller, which implements the non-real-time radio intelligent controller architecture. The near real-time RIC is updated to the current E2 and A1 specifications with 5 sample XApps. And the initial control and data low and high speed contributions to support framework and integration between the DU and the RIC with the E2 functionality and subscription support has been released, as well as traffic steering and quality prediction use case leveraging the E2 interface data ingest pipeline. And finally, OAM use cases that exercise health check call flows in the near-time RIC and its O1 and A1 interfaces. I will also encourage everybody, there's an ORAN virtual exhibition, which has demonstrations of ORAN-based technologies, and the link is provided on this slide. It's a good exhibition to get an overview of some of the ORAN capabilities and further enhancements. Next slide, please. Some of the deployment highlights. It's important to note that Open RAN systems are already deployed. NTT Docomo and Rakuten, for example, have deployments in Japan are very prominent examples. and major European operators such as Telefonica and Vodafone also have been active in the deployment arena. AT&T, we've conducted several demos and trials, including working with CommScope and Intel to demonstrate a millimeter wave 5G G-Node B and open fronthaul, leveraging developments at ORAN, and hosted the ORAN Alliance Plugfest, where Samsung demonstrated multi-vendor compatible configuration performance and fault management capabilities of the O1 interface. Verizon is partnering with key suppliers to conduct vRAN trials as a move toward hardware agnostic solutions. And Dish has entered a multi-year agreement with Mavenir to deliver code-native Open RAN software for its 5G wireless broadband network. As noted here, 22 MNOs have announced intentions to deploy Open RAN-based commercial networks globally. And operators, integrators, and analysts indicate cost savings of between 35 and 49% as the main driver. Next slide, please. The Open RAN Policy Coalition was formed earlier this year as well. And what this will do is promote policies that will advance the adoption of Open RAN networks as a means to create innovation, spur competition, and expand the supply chain for advanced wireless technologies, including 5G. Some of the policies that are promoted, including support of global development of open and interoperable wireless technologies, signal government support for open and interoperable solutions, use government procurement to support vendor diversity, fund research and development, remove barriers to 5G deployment, and avoid heavy-handed or prescriptive solutions. 5G and Open RAN security, really looking at next-generation trust. The open interfaces defined in the technical specifications will provide a foundation and architecture for improving security. And of course, standards play a very important role in defining 5G security and in Open RAN. Slide 12, please. So some of the key takeaways. Future RANs, again, are going to be built on this foundation of virtualized network elements, white box hardware, and standardized interfaces. The ORAN Alliance and other consortia, such as TIP, they are developing solutions that are complementary to standards promoted by 3GPP. They're not in competition with 3GPP, but using and building upon what 3GPP is defining. ORAN should be treated as a zero trust environment, and ORAN security will be defined to follow best practices. Open RAN systems are already deployed, and adoption and interoperable solutions in the radio access network will help create innovation, spur competition, and expand the supply chain for advanced wireless technologies, including 5G. So with that, that concludes my talk for today. Thank you very much, and I'll turn it back to Melissa.
Great, thank you so much. That was very enlightening. I learned a lot about the ORAN, and I didn't realize how many different organizations were involved. We do have time for at least one question. So this is from Pierre, who asked, going from closed proprietary equipment to the open, disaggregated Open RAN model seems like switching from Apple to Android. But a lot of people love their Apple smartphones. So what is lost when one makes this shift? You're on mute.
Sorry about that. Yeah, I think it's a little bit more complex than going from Apple to Android. Yeah, certainly it's a jump in the architecture when you're jumping from a more closed integrated solution to more open distributed solution with potentially different vendors. I think the gains outweigh what is lost. I mean, certainly the testing becomes easier when you have a single vendor solution. You don't have to integrate different components together. So one can think of that aspect as being lost. But I think when you look overall, the gains that you get from moving to the open architecture far outweigh what potentially could be lost.
Great. Thank you so much. Just want to remind everyone to please come back to the breakout sessions at 2:30 if you want to catch Mr. Daly for more questions. So it is now my pleasure to introduce the moderator of our design panel, Dr. Tom Rondeau. He is a DARPA program manager with a focus on adaptive and reconfigurable radios, improving the development cycle for new signal processing techniques, and really exploring new approaches and applications within the electromagnetic spectrum. And prior to joining DARPA, he was the lead developer of the GNU radio project. I encourage you again all to use the app in the program to peruse the complete bio of not only Tom and our speaker, but also all our amazing panelists. And now I will turn this over to our moderator, Dr. Tom Rondeau.
All right, thank you. So I've got a few slides to kick us off here, just to try to frame the conversation a little bit. Rachel, if we go to the beginning here. So we're talking about resiliency at the radio layer. It's a fairly open-ended question in a lot of ways, and that's what I'm hoping to explore here, is to provide some context for, or at least some way to conceptualize what this means. So we just heard about ORAN, which is a fantastic project that I think actually helps capture some of these thoughts that we're talking about here. And then once I go through my slides, I'll introduce we'll go in order through our speakers on the panel. And I think we're going to get some really interesting technical depth on the subject. So I'm going to keep it at the high level as much as possible. So if we can go to the next slide. This is, as I say, an oversimplification of the traditional or the kind of pre-5G, sort of pre-4G cellular model where everything was very discrete. It was very nicely blocked off. You had the user equipment, which was a handset, now our smartphone. You had the base station, you had the core. I'm hiding a lot of details here, but it was fairly separable in a lot of the capabilities. Go to the next slide. Another way to look at an oversimplification of what 5G and beyond cellular networks can look like. This goes back to what you heard from, I know Jeff Reed said it yesterday, Joe Evans said it yesterday, and I think Lisa said it this morning, that this is a revolution. This isn't just a small evolution in from 4G to 5G, that it's looking at the world very differently. And what we're looking at here is a perspective of the explosion of opportunities. From instead of just having a handset, now it's the Internet of Things. This is really kind of it coming to fruition. So all of those different apps and services are now part of this whole space of the network. You've got multiple different frequency bands as we go from low band to now we're opening up the mid band. We've got the high band, millimeter wave stuff. We've got the virtual RAN. It's no longer just a box and a base station. It's virtualized. It's much more. This is the ORAN concept that we just heard about. And then you got the cloud-based core. So everything in the cloud is really, the joke is that the cloud is just someone else's machine, but it's a lot of machines. It's a lot of virtualization of the machine layer doing all the tasks that used to, we used to rely on as again, these individual kind of core siloed buckets here. If we go to the next slide, there's a huge opportunity. And this is what's, I think, exciting about where 5G is going is this growth in application space and the demands that we're going to have for our network. AR, VR is a great promise. I love the idea. We haven't seen the killer app for it yet, but I'm sure we'll figure it out if the network is there to support it. The wearable world, again, kind of been nascent, but again, if the network is there to support us, I think we're going to figure out what wearables really mean for us. Hyperlocalization, and I call this enhanced auto, the vehicle-to-vehicle communications. All these are really cool ideas that the 5G and beyond network is promising. Now, it does come with limitations, though, and that's the power performance scale on the y-axis here. So the more that we push into this future of applications, the harder it's going to be to fit all of that compute power into the power envelope of a lot of these systems that are going to be disconnected from wall power. So it's going to be a battery limited service. But what I'm trying to open up here is both this opportunity, but also this challenge of how much the application space and the demands of our systems are going to come to play here. So as we go to the next slide, this kind of brings us back to what I'm trying to propose here, which is as we've gone through the generations of wireless communications, but you can see this very starkly in the cellular communications world, We had discrete hardware components. Everything was just a brick that did something in the RF world, and it did, process that signal. We then moved into RFICs, integrated circuits, or ASICs, to do a lot of the processing itself. Very walled off, very black box approaches still. Now, though, our modems are much more software defined. They're much more based on very complex but very programmable RF integrated circuits, and you've got the programmability of the modem and the radio layer. And as you push into the core, these two worlds are colliding more and more, from where it used to be everything was specialized to the chip that were built very specifically for the core, to more of that specialized cloud computing that's been the past, at least generation to maybe generation and a half. But now we're talking about cloud processing, and again, this O-RAN, as you just heard about, is starting to look more at commodity cloud processing. So now software-defined networking. So again, software is everywhere. If we go to the next slide, if you remember Mark Horowitz's "Software is Eating the World," well, software is still hungry. There's still a lot of space that software is coming into play here, and it's taking over more and more of our application space. So the point of this, trying to set the stage here, if we go to the final slide here, what I just want to open up here is I like ontologies, or this is more of a taxonomy with a little bit of an ontological twist to it. I'm trying to think of this in terms of what we can look at when we think about resilience at the radio layer, to really what is the radio layer anymore. We can go to the far left, the RF, the resilience at the left. I'm calling them threats, which maybe that's a bit too of a DoD term, because there's more than just threats. There's just issues to deal with. But we'll look at it as threats: intentional, somebody's actively trying to jam you, or unintentional. That's could just be interference or poorly designed systems. But the cyber threats, again, everything being software defined these days, the cyber threats become more realistic. I think I saw Dirk Grunwald in the audience here, so I'm going to quote him and the idea of an RF script kiddie. These are the more easily accessible tools and devices. I'm partially to blame, having led the GNU Radio project, where we built all the open source software to manipulate this type of stuff. You can build attacks very easily. But then you also have the professional and nation state attacks as well. What do those look like in a world where, again, the surface space is all on this programmable plane, interacting with each other? And finally, one of the things that I wanted to point out here is that hardware and software, as I've said, they're so intimately tied together and tied to 5G. There's issues with those that we have to deal with from a security perspective, and to be resilient. It goes all the way back to the supply chain. Where are we getting our silicon from? Where are we getting our software from? Configuration management is probably the biggest flaw of security in home networks, not configuring your Wi-Fi router to have proper passwords and user locking down security configurations. So with that, I wanted to kind of use this as a way to scope what we're going to talk about, because you're going to hear from our esteemed panel members aspects and perspectives that cross this entire spectrum here, pun intended. And while people are talking, I would really encourage. I'm seeing some questions come in already, which is lovely. Really encourage you to ask questions. You're going to get sick of me asking questions if you don't. I really want to hear from you over the next roughly hour. So with that, Rachel, we're going to move over to Alex's presentation. So our first panel member here is Alex Demjanovic, who comes to us from Qualcomm. He's worked a lot on cellular standards, prototyping of networks, leading Mac system design efforts. He's worked from 3G, 4G, and now he's really focused on the 5G new radio standard. And he's going to start us from the radio layer itself and from that RF aspect. So over to you, Alex. Alex, you there?
Can you hear me?
Yes, we got you now.
Thank you, Doug. Do you see my slides?
We do. You want to put them in presentation mode? There you go. Perfect.
So today I'm going to talk about 5G and resiliency at the radio layer with a focus on millimeter wave. So millimeter wave is mobilizing 5G. It's a new frontier for mobile broadband. The available spectrum is huge. It is 25 times more than what is currently being used for 3G and 4G. So in terms of the available spectrum, which leads to higher data rates, millimeter wave offers great opportunity. We are talking about multi-gigabits data rates due to large bandwidth. So we get much more capacity, and because of the waveform design, we also get lower latency. So millimeter wave is giving us a lot of opportunity in 5G, but in order to millimeter wave for millimeter wave to properly function or to basically provide robust performance, we need analog beamforming. So we need large antenna gain both at the transmitter side and the receiver side to overcome the path loss. So that is considered potentially a weakness of millimeter wave because we have very narrow beam communications, and in case of high mobility, the question is if the communication can be robust. However, millimeter wave release 16 now is proven to be during the test, it's proven to have a robust performance. All the beam management techniques that were developed are supporting mobile use cases. So the new opportunities that millimeter wave brings, those are the outdoor deployments and indoor deployments. In both cases, these millimeter wave deployments can significantly improve user experience. The outdoor deployments is typically operator deployed, and initial focus is on dense urban. In case of indoor deployments, we basically can complement existing wireless services provided by Wi-Fi, and we bring superior speeds in cases like factories, for AR, VR, stadiums. So overall, millimeter wave is creating value for the overall mobile ecosystem. For operators, service providers, venue owners, infra vendors, device OEMs, etc. So millimeter wave is part of 5G, and in this presentation, I just want to point out that while one may consider that millimeter wave radio is not robust enough, actually, if beam management is done right, we actually have an opportunity to actually provide an extra layer of resiliency by using millimeter wave. And I'm trying to illustrate it in this figure. Millimeter wave, due to analog beamforming, actually has good jammer rejection. Because of the narrow beams used for communications, in this case, for example, between the G-Node B and the UE, the millimeter wave can provide natural rejection of the interferers. And this interference can be intentional or unintentional. It could be interferer of basically, could be spectrum sharing scenario, where basically we have multiple operators operating in the same band, and by utilizing analog beamforming, we are able to suppress the interference and maintain the communication link. So in case of single beam communications, this suppression comes probabilistically. With a high probability, we may claim that there would not be interference between two communications links. If, for example, we may even have a scenario where by chance we have interference, like just like illustrated in this figure, that scenario can be addressed with multi-transmission point diversity. So, so basically, if one link is interfered, millimeter wave release 16 allows 5G release 16 allows multi-TRP communications, where a device can communicate with two different transmission points at the same time. So this feature provides interference diversity and allows the user to maintain robust communication link with the network, even when one of these communications links is jammed, either unintentionally or intentionally. So this type of feature, due to analog beamforming, can provide interference rejection from strong interferers, because the interference rejection is done at the RF layer. Basically, we can see how this analog beamforming can be utilized to provide actually resilience in terms of spectrum sharing, where multiple communications links are active at the same time. And to conclude, this feature can also be utilized to provide an additional degree of security at the RF layer, because in terms of eavesdropping, it is much harder to eavesdrop narrowband communications, particularly when we have multiple links with the network. And with this, I would conclude my presentation.
Excellent. Thank you so much, Alex. So we're going to move on. I've got tons of questions for you, but I'm going to hold them until the end. I want to hear from everybody first. So next, we're going to move farther into the system design here with Andy Molish, who's a Solomon, Guillaume, Andrew, and Erna Viterbi Chair and Professor of Electrical Engineering at the University of Southern California. Long history in the wireless world, focused a lot on wireless propagation and wireless system design. So recently he's been focused on that combination of the radio and propagation aspects of 5G and beyond networks. So Andy, if we can get your video up, and Alex, if you want to close your video down. Over here. There we go. Perfect. All right. Andy, you good with audio?
Oh yeah, I was still on mute. Can you see the full screen now, or does it show you the presenter view?
There, we're good. Yep, you're on full screen.
Great. Yeah, so thank you very much for giving me the opportunity to being part of this panel. I wanted to discuss a little bit about the question of resilience in terms of problems that nature might throw our way. And so, of course, Alex has already talked quite a bit about the specific aspects of millimeter waves. I want to look at it as you said, a little bit more from an overall system perspective, which includes the frequencies as well. And I guess the first question that arises is, well, what is actually different in 5G compared to 4G? And even though 5G is viewed as a revolution overall in wireless, from a physical layer point of view, there are not really that many differences when we're comparing it, for example, to LTE Advanced. Key differences are really in terms of massive MIMO, as well as in the introduction of millimeter wave frequencies. So when we're now looking at the different possible error sources, we can ask, well, what is different from that perspective? But also, why are we having such a big emphasis on resilience now in 5G? And that's really mostly coming from the applications. So starting out with the possible sources of errors, I guess we're all learned in our wireless courses and textbooks about the small-scale fading. And that, famous last words, I would say is not really the main issue in 5G. And it's assumed in most of the theoretical papers, also because it can be handled fairly easily mathematically. But there are so many small-scale diversity sources, from antenna diversity to frequency diversity, temporal diversity, and so on, that this might not be the main emphasis right now. In particular, when we're looking at the impact of massive MIMO, where we have channel hardening as a key effect, small-scale fading effects go a little bit away. In terms of millimeter wave, in particular, when we have a line of sight with dominant reflected components, the fading depth might not be as large either. And the biggest emphasis might be actually for the transmission of short packets when we're more looking at the IoT applications, because we have a reduced frequency and time diversity there. And we can think about physical layer techniques with which to circumvent that as well by, for example, going back a little bit to spreading techniques in frequency and time domain. Now, the bigger issue seems to really arise from the large-scale fading. And I actually want to say that question of resilience, I encountered that at least 15 years ago when I was at Mitsubishi Electric Research Labs, and one of the big questions there in factory automation was that the people building the factories wanted to have 5 to 7 nines reliability. And so the question of building ultra-reliable networks to protect machinery that might be millions or hundreds of millions worth, that is really a big factor. And the thing is, with a single link, it essentially is impossible to achieve these level of reliability. I think this is something that we are seeing nowadays very much in 5G, something that Alex has also alluded to, that we simply need multi-base station or multiple access point connections to our different to the various devices, because the shadowing due to environmental objects and so on is going to kill us. Now, as we're going to higher frequency ranges, in particular, body shadowing by a person or a robot holding a device is becoming very relevant, because now we're starting to look at the spatial correlation or the angular correlation of the shadowing. And even if we have multiple access points, they might all be shadowed off at the same time if there is a big object standing right in front of the device that wants to communicate. So this is having a major impact on millimeter wave systems, and also we're becoming more sensitive to these effects in ultra reliable low latency systems, because there is really no time to correct. Even if we have a dynamic shadower, if the shadowing lasts for about a second, but we have a requirement that the packet goes through within 1 millisecond, then we obviously have some problems. Possible solutions out of this dilemma are to go to multiband systems where we might have, for example, a low frequency system that has maybe lower data rate but can easily diffract around obstacles as a sort of fallback solution that can at least communicate the key data while a millimeter wave link might be shadowed off. We are dealing with another source of error in terms of delay spread, which of course is caused by multipath, and which can be viewed as an advantage. But now, as we're getting to data rates of 100 gigabits per second or more, delay spread might actually turn into a drawback, because we simply don't have the equalizers or don't have the processing capability for OFDM to handle delay spreads that are hundreds of symbol durations long. Beamforming and analog equalizers might be some ways of how we can get around this problem. Another new noise source that we are encountering, in particular at millimeter wave systems, is phase noise. And of course, Doppler also falling into that category of unpredictable phase shifts. And so this clearly becomes more relevant as we are going to higher frequencies. We pretty much get a linear scaling there. And we have to think carefully about what are the possible countermeasures. That's really something. Phase noise has not been an issue that at below 6 gigahertz has bothered us very much in the past. Another challenge we need to handle in terms of robustness, it was already mentioned that, of course, beamforming is a very important part, both at high frequencies, but also at lower frequencies when we're dealing with massive MIMO systems. And the key question now is, how quickly can we adapt our beam weights as the transmitter or the receiver is moving around. This might be partly a question of how often do we have reference signals, how fast can we do the feedback, how precisely can we do the feedback, but then also when we have dynamic obstacles, then that might be blocking our preferred directions, how quickly can we actually reconfigure and completely retransmit beams into different directions because our main beam has been blocked. The protocols that are foreseen in NR are a little bit on the slow side. We did some simulation work together with Sanjay to see how fast could these things happen. And there is certainly still room for further improvement and research. Could be via compressive sensing, could be via exploiting machine learning in order to get a better estimate of where to put our beams. Last but not least, the question of interference within the system and coverage. So one of the key challenges we encounter, of course, in millimeter waves is that streets that have a particular orientation might be very difficult to cover because the waves essentially would have to diffract into the street, and millimeter waves don't like diffraction. So we could think about new countermeasures, including 3D network deployment, so that we're essentially exploiting the possibility of drones as temporary base stations or balloons or satellites to complement and fill out the black spots that we might otherwise have on our coverage maps. And we also have to consider the question of interference, which of course is becoming critical for high density deployment, where we are now looking at self-read massive MIMO provide less interference and microdiversity. So in summary, we have a number of new challenges for the resilience in 5G, which is partly coming from the fact that we're using different frequency ranges and larger arrays, but also from the fact that we simply have more stringent requirements in terms of our quality than we had in previous systems. Maybe one last point that I want to mention is that the analysis of how bad the situation is also very difficult because we do have standardized channel models for 3GPP, but those are really only suitable to compare one system against the other. If we want an absolute performance evaluation and say, what is the likelihood of an outage with a system, then the 3GPP channel models are not suitable. And you can just imagine that if you want an outage probability of 10 to the power of minus 5, then you have to have enough channel measurement to actually assess how likely is it that a 10 to the power of minus 5 event is going to happen. And if you're just saying, I have 100 points, I fit really to it, and then I guess that that's also going to be valid in the tail where the 10 to the power of minus 5 point lies, then you might not be getting a very good
Andy, not sure if it's just me, but we lost your audio.
I still see myself.
You're good. You're back now.
Okay. So maybe that was a sign from above that I should stop talking. But I think you saw my key summary here now on the last slide, and I'll hand it back to you, Tom.
Excellent, thanks, Andy. And yeah, you actually preemptively answered one of the questions about the channel models and are they relevant for millimeter wave? And I think that is an interesting challenge. In fact, one of my running jokes about 5G is that it's like Star Trek movies that only the even ones are good. So what you're posing here is a lot of questions about what there were a lot of questions that need to be answered, but they need to be answered based on the needs of the application space. So there's a lot of things that 5G is pushing out there that aren't necessarily based on needs from the consumer or from the market space of applications that are going to be developed. But I think that they're going to go hand in hand. We're going to develop those applications. We're going to develop those new markets, learn what they actually need, and then your questions become relevant as far as how fast do you need to have adaptive beamforming? How many beams do you need to support? Those kinds of, and what the fading characteristics do versus those needs. So I think it's a fascinating way to frame the problem that I think really will help us lead to the answers that 6G is going to require from us. So thank you. So more on that later, but let's move on to our third speaker, Kumar Balachandran, who is a wireless communications engineer with Ericsson. He's got a long history of work in all areas of the mobile communications stack, including the physical layer, signal processing, radio resource management, spectrum sharing, protocol design, and systems engineering, all the way from 1G through now 5G. He's also an active member with the Wind Forum and serves on the FCC's Technology Advisory Council. So if we can get, Kumar, your video and audio up, I'll hand it over to you.
Yeah, can you hear me?
Yes.
Okay, great. So I think to start with, we like to think of the entire problem of trustworthiness, from a systems viewpoint, and to look at resilience as one aspect of what we need to consider going towards trustworthiness. It might be a good idea to just step back and then define what we mean by trustworthiness, right? In reality, a system's trustworthiness is really composed of a complex and holistic view of the integrity of the system. Now, the reality is that these views of system trustworthiness actually cover non-technical areas such as business processes, customer appreciation, the actors in the ecosystem, as well as regulatory dimensions. There's no doubt about it. But it's very important for us to gain control over the technical aspects of the system that can solidify the attitude of the system with regard to specific requirements. So the technical basis for trustworthiness in a system consists of those aspects of trust that are derived from measurable or attestable evidence of compliance to requirements on aspects like security, reliability, privacy, availability, safety, and resilience. And in this systems view that I have up on the screen, you can see that this is actually a process that spans all the way from development, which starts from standards development to R&D, and various aspects associated with it, possibly regulatory requirements as well get into it. There's a deployment and configuration or reconfiguration of the system. Both of these are sort of related to each other by supply chain aspects as well as continuous integration and continuous development processes. And finally, there's the operational aspect, which is really important, which is that you have to have enough observability in the system by means of measurement, the ability to analyze what's going on, and to detect anomalies and respond to them. And basically, the idea is that now you have this threat and risk landscape that is acting on your system, and this is constantly changing. And you have to derive some sort of a composite idea of how your system is behaving at the top side. Another way of looking at this picture really is using some sort of a trust stack, where you look at trusted nodes and products right at the bottom layer of the stack, and then you go on to a trusted network, followed by operational trustworthiness, and finally how much you trust the business aspects of what you're providing. We can go to the next slide. So we really like to look at resilience as something that is derivative of the availability of the system on the network side, as well as the reliability that you have. And this has implications for the physical layer, just as well as other locations in the network, as well as other layers of the stack. And in 5G, you can look at approaches to this phenomenon that we call NRAR, using techniques like node pooling. One aspect that really comes out of this is the fact that when we justify the development of a new generation, we're really looking at traffic projections or use case projections, and then saying, okay, we really need so much spectrum to handle the number of users and the amount of data that needs to be carried in the system. But when you want reliability and resilience, a lot of it depends on how much headroom you have. So it really depends on how much abundance of resources you're able to add to the system so that you can trade off coverage and system capacity towards establishing the kind of resilience that you require in your system, both to intentional as well as unintentional threats. And of course, there are new 5G core features like network slicing and virtualized network functions and service-based architecture, etc., which each provide certain facilities, but the way you use those facilities to achieve the basic principles of enabling trust in your system and resilience in your architecture is important. And now, physical layer resilience is really aided by design for reliability. This means you have to design for coverage. In 5G, we have this notion of a lean design for control and signaling channels. The robustness of the signaling and control channels are much greater than what you have for traffic. We have the ability to deploy spatial diversity with MIMO, beamforming, densification of networks, etc. And these are all tools available, again, that you can use towards creating a resilient design in your system. Now, of course, every time you add new use cases or new applications, you create new threat or risk surfaces to your system. And every new performance requirement in this sense ends up being a potential risk. So if you take 5G applied to critical communication needs such as industrial automation and so on as one area, then you can identify the reliability requirements and latency requirements for industrial applications as being a potential addition to your risk landscape. And you need to handle that in your design and deployment and operational strategy. Now, old risks still remain. The fact that you have to have backward compatibility with previous versions of the standard means that you inherit some of the vulnerabilities that you have in previous standards. So, for example, with NR, the fact that you're deploying NR in a non-standalone fashion initially will definitely impact the attitude of the system with regards to the same vulnerabilities that you might be able to identify on the LTE side. And new features in 5G, of course, they do eliminate some vulnerabilities. There's integrity protection for signaling since 4G. That's been available since LTE. And then now with 5G, we have dynamic placement of signaling. And of course, now a lot of the signaling and control channels are dedicated, which means that you can apply beamforming to them and thereby increase robustness. And we have reduced the amount of dependence on broadcast and common signaling towards large groups of users. It hasn't been totally eliminated, but it's definitely been reduced. And then there are subscriber privacy enhancements, the use of confidential physical layer identities, the subscriber concealed identifier, SUKI, the independence of the paging identifier from permanent identities, and the fact that since 3G we have had mutual authentication of network access with the user and so on. These are all benefits that continue to improve the system. Next slide. So we might ask the question, how robust is the 5G radio link? And the answer to this is that, physical channels can always be compromised with excessive interference power relative to signal power. And so what does 5G provide that mitigates interference susceptibility? We have advances in channel coding that have been implemented, the use of LDPC and polar coding, for example, the use and maybe even dependence on advanced antenna systems provides you with some flexibility. And then the signaling channels are really designed for good coverage. I mean, it takes incredible amount of interference to compromise a signaling channel. And then the link budgets, when you calculate it, they can provide you ideas about the coupling losses for each logical channel configuration with the associated key performance indicators that's associated with it. So for example, some of the signaling channels will have greater robustness because you have access to higher antenna gain in those modes, versus other signaling channels where you made use of channel coding as a way of improving the interference resiliency and so on. And in general, you can also use system configuration to aid more robust design and deployment. So we have we have a pretty strong recommendation to operators around the world to initiate identity handling with this concealed identifier that I talked about earlier. And for NR standalone, which I understand most operators, at least in the US, are very motivated to deploy quickly. Network slicing can improve robustness by preventing fallback to 4G and prior generations if the use case demands it, right? And there will be a certain compromise with coverage if you decide to do so. And of course, future releases will likely allow integrity protection for the data plane, and that can be, activated for certain use cases if it's needed. Now, there is some susceptibility analysis available in literature around jamming performance. For instance, Lichtman et al. I've given a reference in the slide set if you get a chance to look at it later. One of the issues that we noticed over here is that this work really analyzes jammers operating in the energy limited region rather than the power limited region. And operationally, it's really the power limited operation that is relevant, mainly because of the level of flexibility you have in arranging signaling and in 5G. That makes it very difficult for an adversary to figure out, exactly where to put the interference. It takes a very intelligent adversary to do so. And in effect, the amount of power that you have to expend to completely compromise a signal is quite large. But in reality, you have to conclude this slide with saying that mobile networks cannot be made totally resistant to jamming. Best we can expect is to increase complexity, improve diversity opportunities in your network, and maximize energy consumption by adversaries to prevent them from compromising your operations. So, for example, cross-carrier scheduling and other aspects really come into the picture. The fact that you can operate over so many different frequency bands, etc. So to summarize, trustworthiness is largely derived from that part of trust that originates from evidence of compliance to well-defined requirements and processes pertaining to security, reliability, privacy, safety, and resilience. And physical layer resilience especially is derived from reliability and robustness. And it can also involve system adaptability as a mechanism, especially if you have access to a level of sophistication in the observability that you can introduce into various parts of your network. And additionally, it's achieved by a design that focuses on coverage, exploits diversity and redundancy, encrypts information and protects integrity, and generally provides multiple diversity opportunities in the channels that you use. And it's important, very important, to couple system observability through continuous measurement analysis and inference. This is an important area for application of, for instance, machine learning, because of the sheer volume of data and diversity of data available in various parts of the network. I'll stop there.
Excellent, thank you, Kumar. I was with you for everything up until kind of the end of the previous slide. I think you're right. It's a system perspective. We have to look at the whole thing together. But I think you're overestimating the sophistication and intelligence required to disrupt a wireless network. I think it's a lot more susceptible than what you showed there. And we can maybe debate that a little bit later, get into some more details. But that was the one thing that I picked up on, that a few of us in the software radio world have found lots of ways to cause havoc if we really wanted to. But otherwise, I think you saw Kumar kind of sits in the middle here, looking over the entire stack. So let's move a little bit further into the system, into the core itself. We're gonna have Pam Patton. We can get her up. So she's a senior communications engineer at the Johns Hopkins University Applied Physics Lab. So I'll probably just be referring to it as APL. She's a technical lead for the 5G wireless communications lab, looking at networking architectures, virtualized cores, and this extends from her previous experience with 4G LTE, both at the lab, and many years of experience in wireless communications for the Department of Defense. So she's going to talk a little bit more about some of the key vulnerabilities that she's looking at for 5G.
All right, thank you for that intro, Tom. Let's go ahead and go to the next slide. So this is just to give you an idea of like where my brain is at, why I think about 5G the way and some of the problems is mainly from the point of view of our customer set at Johns Hopkins University Applied Physics Lab. So we're a university affiliated research center, and we have 6 pillars of focus in terms of communications within our asymmetric operations sector. The first 3, nuclear command and control communications. We look at satellite communications, and then cooperative engagement capability and data distribution systems. And then the next 3 is where we really look at, this is where 5G comes into play, is looking at the senior leader communications and how do we secure communications in critical missions. And cellular is a very good tool for communicating on the move, and how do you make that more resilient and more secure. We also have in the next pillar is special users. You can look at tactical users, military. How can you tailor cellular systems to meet the needs of those special users? And then the last pillar is advanced communication technology development. And this is how we look at 5G from the point of view of software-defined radios, looking at those GNU radio, open source, and some of those custom software-defined radios, and how do we use 5G in different ways or different parts of 5G to meet the needs of our sponsors. So this kind of gives you an idea of how I'm looking at 5G for this panel. The next slide, please. So this kind of sets up in terms of our focus on RAN. So a majority of, if you look at the 3GPP standards and the technical reports that have been coming out for release 15 and release 16, a lot of those security features are focusing on the network side rather than looking at the RAN side. They focus on integrity, confidentiality, and authentication, which is very important. But we also don't want to forget about the effects of interference, intentional and non-intentional, that will affect the resiliency of, again, this is a whole system, right? So you affect one part and it affects everything. In order to protect one part, you need to put security in all the different parts of that network. So how do you address that RF interference? So again, looking at those specifications, mainly at 33.5, 501 is more on the architecture, looking at those interfaces between the F1 and the E1 interface, and those are within the RAN, but that's more on how do you protect the protocols within the RAN for your integrity protection and against replay and confidentiality. Then if you look at the technical reports specific to release 16, there's a study on 5G security enhancement release against false base stations. And again, you know, that was mentioned earlier. This is a known problem since as long as cellular has been around. Obviously, AMPS, you just need an FM receiver. But once you got to GSM or 2G and above, you know, these false base stations were becoming more and more easy to reproduce. Now they're really cheap hardware and really cheap software, so you see a lot of the base stations. But pretty soon we're going to start seeing UEs that are going to be emulated on those software-defined radios. And then how do you address a UE that you don't trust, rather than how do you trust a base station that you don't trust? Let's go to the next slide. So I figured I would frame this around a specific use case. And like I mentioned earlier, that use case of an uplink or an untrusted UE. I'm glad Brian Daly went before me so he could describe a little bit more detail about those O-RAN interfaces. And what I have here with those blue arrows that are pointing up in between the central unit, the distributed unit, and the radio unit, that's kind of where that E2 interface from that RAN diagram that has that near real-time RAN intelligent controller or that near real-time brick. How that can be put into play to make this RAN over-the-air interface more resilient by responding more quickly and autonomously, rather than sending, you know, key performance indicators back to a centralized OSS or BSS or some sort of management plane. Have that base station or that RAN radio network act independently based on what they see at those different points. So in this example, you have these rogue UEs, machine type communications or IoT, that are flooding maybe one or a couple of towers. You know, you see a lot of security papers about IoT and, you know, refrigerators being taken over and toasters taken over to take down Netflix or some other content delivery network. But in that process, if those devices are geographically located in the same area, they can also flood the RF with too many radio channel requests or like a ratch attack type of scenario. And in that case, they're taking out not only, you know, the content delivery network that they targeted, but they're also taking out other users. So how can you use that real-time intelligent control plane to look at that data over time and do some, you know, analysis, whether based on like machine learning or artificial intelligence algorithms, to look at this traffic and then see at the RF level that, hey, there's something unusual happening, rather than waiting until all that data gets processed into IP packets and then sent back to the core, that then you have to do your intrusion detection and filtering when that data has become overwhelming. So moving that threat detection to the front, through the RAN, can also make your network more resilient at the OTA layer. And this architecture doesn't rely just on O-RAN. If you look at most of the 5G radios that are coming out, whether they're separate cloud-based processing units or they can be separate cards within a chassis, they still have those F1 and E1 interfaces, and you could still monitor the RF level or layers for traffic and anomalies at those different points within the processing chain. It might be within a backplane, within a single chassis, or it can be distributed. So that was just a really high level, but I just wanted to put out, a possible use case of how that O-RAN could be used for increasing resiliency on a 5G network specifically. And I'll hand it back over to Tom.
All right, thank you, Pam. What comes to mind with this one is, you and me are coming at it from a fairly national security and defense perspective, whereas a lot of the KPIs in the specifications are going to be commercially motivated. So your example here, it's interesting to start thinking about what are the risk mitigations and the attack surfaces from the national security versus commercial. How do they intersect? Where do they diverge? And therefore, what's the role of DARPA, APL to help understand those if we're going to use this for national security purposes? So, fantastic way of thinking there. So, okay, great. So we have one speaker left. We're going to bring him up now. So, Serge, so he is a program manager at DARPA's Microsystems Technology Office. I used to be in that same office together until I moved to Stowe. But so he joined DARPA from Mentor Graphics, where he's a vice president of new ventures. He's been running programs at DARPA related to supply chain trust and assurance. Also some open source design tools for better EDA, so basic chip design and building. But I think he's going to focus on that supply chain in the 5G world for us now. So, Serge?
Thank you. Can you guys see me?
Yep, you're all good. Let's put it in full screen mode, if we could.
I'm not the one controlling that.
Rachel, yeah. And
maybe you should hit enable editing and then go full screen.
Yeah. So, Serge, why don't you go ahead and begin, and I'm sure Rachel can.
Yeah. Hi, thanks, Tom, for the introduction. So I focus on EDA and computer architecture type of programs and hardware security. Is my video up or not?
Your video, you are up. I think we're still working on trying to get the slides presentation, but I'd encourage you just to keep going so we can.
Should I try to share my screen or?
Yeah, why don't you go ahead and try to share your screen? If it comes up quickly, we'll move. We can do it.
Is that visible?
It's coming. Perfect.
Okay. Anyway, so my. Yes.
One second. It's cut off. It's not showing us the full thing. So why don't you escape? You know what? If you can just minimize like the bar on the left, let's just go with what you got here, and let's just keep moving.
Like this?
I think that should be good. Yeah.
Okay. Thanks, Tom. So basically, what I wanted to talk about here briefly is the program called ACE, Automatic Implementation of Secure Silicon. And while the original plans behind this system were not specific to 5G, but the intent was to look at
securing edge nodes in general. So edge nodes, whether they connect to Bluetooth or Wi-Fi or 5G, are all sort of part of the scope here. And so the objective of the program is to automate the inclusion of scalable defense mechanisms into chip designs to enable security versus economics optimization. So if 5G is truly pervasive, then it can be compromised not only at the network level,
but obviously at the edge or in a data center. And so the chips themselves that are used to implement data center or the edge node is what we're thinking about how to protect. And so in hardware security, there is not a single solution because all the security strategies come at different price points. To liken this to real life example here, sometimes putting a lawn sign declaring your affiliation with a security company is enough to dissuade some attackers from hitting your house. And then in some cases, even Fort Knox defenses are not sufficient to discourage those kinds of attacks. So in ACE, what we are trying to do is we're trying to come up with next generation design tools that incorporate security of chips right into the design implementation flow. So there are three prongs here. One is on-chip security engine. And on-chip security engine is a component that we're adding to any chip that will essentially allow enrollment, authentication, provisioning to ensure authenticity of a particular device, but we can also monitor execution and enforce security policies as the chip runs. We also are working on tools that would be used during the design process to secure the designs. We can obfuscate certain parts of the chip so that it is resistant to reverse engineering. We can watermark pieces of logic that are used to put the chip together, or IP. We can try to do simulation of possible side channel attacks and other kinds of attacks. And we can analyze threats and vulnerabilities. And then to put all of this together, there is the automated integration process that occurs, which is essentially system synthesis. And here we need silicon platforms, generators, interconnect, and we need to optimize all of those things together. So you guys largely come from software. So if you look at my next slide, I'm sort of ignoring the software side threats because it appears that more than enough effort and expenses going into those, into addressing those threats. And the next level of cybersecurity that we're cognizant of on my team is the hardware-software interface, and there DARPA in general and MTO specifically has activities in this area to protect the hardware-software interface. What I'm focusing on is specifically hardware security. And hardware security falls into these four categories that we are addressing. One is side channel attacks. This is where an adversary tries to extract secrets from the chip using physical communication channel other than what was intended by the designer. And here we're making relatively conservative assumption that attackers are actually able to listen to what our chip emits during execution. So in other words, this assumption forces us to build more intense protection strategies. Reverse engineering is another attack surface that we worry about, which is extraction of algorithms from illegally obtained design representation. This could be a chip that's sliced into layers and then reassembled using rather invasive techniques, or somebody simply walking out of some building with design files. Supply chain attacks are a big thing as well. So here we worry about cloning, counterfeiting, recycling, remarking of the chips, and then representing them as genuine articles. And here the assumption we're making is that attackers can manufacture perfect clones. That means our defense has to be robust enough to deal with that. And then malicious hardware. This is also referred to frequently as hardware Trojans. This is another attack surface that we need to protect, and that is insertion of secretly triggered hidden disruptive functionality into the design. And here we're making assumptions that the attackers successfully inserted malicious function into the design. And so our defense strategy sort of starts from there. So why are we doing this? Who are we trying to help with this? So huge merchant semiconductor companies like Intel, Broadcom, Qualcomm, they already have huge investment in hardware security. They have large engineering organizations that are working on this because solving the chip level security issue is a business critical care about for them. And then on the other side of the spectrum are systems integrators, so people who create IoT edge devices connected to the web and deliver some kind of vertical application benefits. So like security or fitness or intelligent locking of doors. And so those people really don't have any interest in security today because they have very short time to market and it's not an in-house competency. Between those two are other constituencies like mid-sized semiconductor and system companies. And these are companies that recognize the existence of vulnerabilities but do not have sufficient expertise or economic motivation to do much about it. And then there are defense contractors. They typically possess deep but limited expertise. They view it more of as an art than science that is unevenly applied to those designs. So with ACE, we target the latter two groups. And if we solve their problems, then we can make a value proposition to large semiconductor companies that they don't have to spend quite as much effort to make their chips secure. And we can make an argument to system integrators that inclusion of security and its pervasiveness into the design, it comes at limited cost. So what we're trying to do here is actually do system synthesis. We're trying to automatically generate a chip that implements all the functions necessary for a particular application. And since the late 80s, we've been able to synthesize chips like this and optimize them on this performance versus size curve. And so that's been approximately the technology that's been used from 1988 until roughly the present. With ACE, we're trying to add the notion of optimizing for power and the notion of optimizing for security. So, and within security, we have actually 4 attack surfaces. So in essence, we're trying to transition here from 2-dimensional optimization to 7-dimensional optimization in order to come up with a design that represents an ideal set of trade-offs between chip economics and security considerations. There are some big challenges here. Like, for instance, we don't really know how to quantify security. We do not know how to rapidly estimate how one architecture is more resistant to attacks than the other. And of course, the multidimensional simulation is a significant scientific problem. So the way that ACE is envisioned to work is that the starting point is a platform, which is vertically oriented aggregation of parameterizable IP blocks. And then the designer essentially supplies the importance ratings to each of the parameters. So how important is performance, how important is size, how important is power, and then how important is it to defend against particular attack surfaces. And then what the system does is it goes through combinatorial optimization to explore huge spaces of huge architectural spaces. And for each one, it estimates the level of goodness as measured against the cost function provided by the designer, and essentially optimizes for performance, size, power, and security. So, you know, how might one think about this? So you could think about this particular applications that I listed as examples. That, for example, lawn sprinkler, the performance is really don't care. Size is sort of important if you're going to do volume manufacturing. Power is really important because you maybe want to run this thing to run for 12 years on a single battery. Security is like, who really cares if somebody knocks off the lawn sprinkler. But if you think more closely below how to expand the security equation here, you could say, wait a minute, there is actually an attack surface here, which is a supply chain attack surface. Because if my design is successful, somebody could actually clone or counterfeit my chip. And so, no, I do care, after all, about supply chain attack surface. So I'm going to give it a 9. In response to that, this system optimizer will create a different architecture that has supply chain attack resistance capabilities. Obviously, if you're thinking about guided projectiles or routers or automotive engine control applications, the cost functions are quite different. And in fact, for 5G clients, they may be dramatically different from what I have put into this example. And for switching and networking systems, that could be something else entirely. So anyway, I don't have an official summary slide, so I'll end it right here and say we are working on securing chips. These chips are going to end up in your ecosystem, either at the client or data center or network fabric phase somewhere. And so so security of the chips in that whole chain is important, and we are trying to move the science forward in this area quite a bit in Durban.
All right, thanks.
Stop sharing. Yep.
All right, so we only have a few minutes left, but I'm gonna take a little bit more time before we go into our respective rooms afterwards, because I want to get at least a couple of questions in here. But of course, this is just what you get when you have deep thinkers spending their time trying to talk about a very complex subject. So first, there was the most popular question that we got, and I like it. The answer is easy. So when I'll ask it, and then I want to think about the depth of what the question is really asking here about how do we do it. So with the behaviors of software-defined radio, cognitive radio, and then the new radio, et cetera, being increasingly controlled and perhaps dominated by software, there seems to be a need to revisit the equipment certification process, possibly expanding the process to address software. Any thoughts regarding re-engineering equipment certification process? I feel like the answer is we're all going to say yes to some extent, but let's try to dive into what does that actually then mean? And also, some of us who went through the software-defined radio certification nightmare in the FCC about 15 years ago, and how bad that turned out, I would say, and how ineffective it turned out to be, I think. So do we have any thoughts on re-engineering the certification process given software as a dominant factor? I'm just going to keep opening it up to anybody in the participating here.
My own view is it might end up being a lot more difficult than we imagine, because software demands to be very flexible. And if you want the flexibility of being able to change your features and functionality on a rapid deployment basis, then it becomes quite difficult.
Yeah, and as people maybe are processing this, one of the things that I forget who it was now, it may have been Jeff Reed that I was talking to. Somebody brought up the fact that hardware eventually is limited by physics. Software is limited by theories of computation and numerical processing. We have the halting problem. So math is not complete, it's not consistent, and it's not decidable. From those three principles, software is by its very nature dominated by the potential for bugs and flaws that can be almost impossible to suss out to the nth degree. So you're focusing now on this space that is this massive opportunity of processing and mathematics and how that translates itself into the physics of processing electromagnetic waves, coming with all those challenges. Any other thoughts?
So I would maybe argue that there are two separate problems. One is to make sure that the system is doing what it would be supposed to be doing and functioning properly. And the other one is to avoid that it's doing something terrible. And that maliciousness, at least when it comes to the RF emissions, because one could think about mandating certain emergency brakes that could be tested in a relatively simple way. That there are interfaces that we're saying, okay, imagine somebody has hacked into the system. We're giving now the order to send out 100 watts per 10 megahertz over a 1 gigahertz bandwidth. Will the emergency brakes work properly to prevent that? And maybe that's a small enough space that can be actually tested. But I think if we're looking at all the millions or billions combinations of what could in principle happen in a base station and all the software that's running with it, and to ensure that every single possible use case and bug can be discovered in such a certification process, I think, not being a software person myself, but it just seems to be a very difficult notion.
You can, to a certain extent, I suppose, introduce traceability into the system to the extent that any software that you deploy is properly attested and is associated through some chain of trust to a hardware root or something like that. The other aspect of it, of course, is that you can do the same thing for configuration changes that affect the operation of the system. So if there is a command to get your radio to do something, you have a very clear ability to trace who did it and when it was done and how it was detected.
Yeah, I think interfaces is a really interesting one. I think the ORAN Alliance and the work that they've been doing, and as even in the DoD, we've been focusing so much more on open interfaces. I'm a big believer in open source software, my background and everything, but open interfaces are probably more important because it allows you to have constraints, mechanisms built into how things communicate between devices. So it's more of a pluggable architecture. What's happening inside of that could be opaque or work on, but as long as you're kind of gatekeeping between the systems, there seems to be some value there as opposed to the huge problem of just trying to solve the whole software problem. So I think one last question. It was a multi-parter, really to Kumar, but I think other people will have some opinions. I think Pam for sure. This was about KPIs, key performance indicators. So the operational system capabilities. There's talk about the names of 3GPP standardized key performance metrics or KPIs. There's no coincidence KPIs are used by wireless carriers to measure performance and keep their networks running smoothly. In a zero trust cellular communications environment that is like a physical and virtual RAN, the core network, what types of KPIs describe trustworthiness? And is something called that considers trust to be a necessary part of a wireless network?
So the short answer to this is when I presented it, I didn't really intend for the KPIs to be limited to what 3GPP defines. And one of the aspects of what's happening with 5G and with the system architecture is that we're moving more from a telecom-centric approach to building systems to a more IT-centric approach, if you want to look at it that way, because of all the virtualization and the separation of software and hardware and the ability to centralize control and create action at remote locations, right? So a lot of the wonderful work that NIST has done, for example, with all the cybersecurity recommendations and so on, they're still valid. And we really have to, take our learnings from different sources and try to integrate it into this composite that I talked about, so that you have an ability to continuously adapt and develop the system towards, creating the right ability, right level of trust that users and governments and operators can have in the system.
Yeah, and I appreciated your the chart that you had. That was basically a DevOps cycle. So So that concept of having to take an IT perspective on a lot of these things. Pam, I do want to pull you into this because, as I said, there's different motivations here between government and DoD versus commercial, and the KPIs. When you read their motivation, are very relatable to the commercial drive behind this. And they tend not to. They've lagged at least. I don't want to disperse them too much, but they've lagged in security and trust and the things that we in the DoD take sometimes over seriously to the detriment of actually getting solutions fielded. So how do we balance this from your perspective?
Yeah, that's a good point. Because with security, there's cost, right? And so when we want a network to be really secure and really resilient, for those edge cases where those machine type devices go crazy, or some sort of flood signaling or flood attack happens on that network, how often does that happen, right? So the probability of these events happening and how do they affect the overall economics of that network? Is it worth investing on a commercial network? Obviously, for a government-owned network and private networks, it's like, hey, let's throw as much security as we can at it. But also in terms of the KPIs for trustworthiness, I've never actually thought of it that way because I always think of key performance indicators as something real-time telling me what's happening right now. I'm getting this many RRC connections failed, this many handovers are failing. So in terms of trustworthiness, I think that in terms of design requirements or key performance of the design or key parameters of a design that would make something more trustworthy. So I'm not sure if during the operation of a system, could I say it's more trustworthy right now than when it's loaded with traffic? So I'm not quite sure how to answer that question in terms of KPI trustworthiness. But yeah, there's definitely a balance in terms of security, cost, and usability too, right? If your algorithms start detecting a flood of traffic and thinks it's an attack, and it's actually just a bunch of people stuck in traffic, and they're all trying to make phone calls. Now they've all been denied unintentionally by the system. So there's all those trade-offs between security and how you apply that. But I definitely see in those private networks and those government-owned networks that the security is going to be much higher and much more flexible. The commercial networks, again, it's that what's the likelihood of it happening, and then what's that cost?
Yeah, I think it's a really thought-provoking question about what does trustworthiness mean, what does trust mean. So, I'm not surprised we didn't have an answer, but good thoughts, at least good discussion. I want to wrap up, I think, right now, so we can get on to our whatever they're called, breakout rooms. But I do want to wrap this back to Alex and kind of put you on the spot for a second, because I thought the way that I bookended our discussion here was starting at the RF layer and going back into the hardware and the supply chain and the surge. But the thing that always strikes me, and I've talked to the folks at Qualcomm a lot about what you're doing in the millimeter wave, and it's fascinating how much more, though, even though we posed it as an RF problem, the nature of the network in order to manage the beamforming and the multiple base stations required to maintain that connectivity, it is, again, that merge of the radio physics and the antenna physics, but with the networking control and the algorithms required behind there. I think it's a wonderful opportunity to start breaking outside of our boxes, as how we're taught as electrical engineers. You do information theory, you do comms theory, to thinking about this as we really have to be thinking about the whole system. So can you give us more about what Qualcomm is thinking about in terms of aligning itself with the networking function to solve some of these physics problems?
Well, I agree that it's a complex problem, and it has to be looked at not just from the physics point of view, but also the network has to. It's a critical component of millimeter wave system beamforming. So while analog beamforming provides an advantage to basically compensates for the path loss, the beamforming is critical to actually to be maintained. I mean, beamforming has to be maintained during the ongoing communications, and mobility plays here a significant role where we can kind of get in and out of coverage fairly quickly. We can have blockages and so on. So in that regard, very fast and robust beamforming together with diversity. So we talked about multi-transmission points. So we should be able to connect to multiple points and to densify the network so that the UE always has basically a point in the network to connect to, and to minimize latencies when we hand over from one beam to the other. So millimeter wave can actually work pretty well. It can provide huge data rates, but one has to be very careful about the beamforming and the ability to achieve diversity in these networks. So that will make millimeter wave even more useful because of the potential it provides for high data rates. And on top of this, we would have network sharing. Spectrum sharing. So basically, we can, because of the robustness that millimeter wave offers, we can now maybe allow multiple operators to deploy on the same spectrum in the same area, and just line on beamforming for simultaneous communications. So that's yet another layer of efficiency that millimeter wave can bring.
Great, thanks. Yeah, if we were in person, we'd get up there and start whiteboarding some thoughts here about really trying to nail, get into the depths of the questions here, really the math problems that are presented with all of this. But unfortunately, I'm going to close this out right now. I want to leave us with two questions. I don't want to, we don't have time to answer them, but I want to kind of prep them for maybe the breakout sessions, or just to get people's thoughts, because I think they are interesting. The first one was specifically to Serge, but I think it's a general problem that we just talked about in the KPIs. So, Serge, how is trust security measured for a circuit design? So I think we already were talking about it from the trust and KPIs, but also trust and circuit design. Just trust in general is an interesting metric that we could think about. And then another question was, are companies already making 5G related chips, keeping security functions in their design criteria as elaborated here? So again, I'm not going to ask for an answer for that one, but I think, just kind of thinking about it. Serge, maybe since you wanted to speak, I'll give you 30 seconds, and then we'll wrap it up.
Yeah, Tom. So basically, there are metrics associated with each attack surface, and so it's not a simple answer. This is the security of this chip equals X, and security of that chip equals Y. So, for example, for reverse engineering attacks, how many combinations of keys would it actually take to crack a particular logic obfuscation, logic locking scheme? Is it 10 to the power of 27 or 10 to the power of 45? That's a metric. In side channel attacks, also the degree of emissions visible outside the chip is a metric as well. As to whether 5G makers are employing any of these techniques, I would say that at this point, the truly advanced on-chip security methodologies are only in use in the very, very largest of merchant semiconductor companies. And just about anybody outside of those two or three, I would say, is not using the most advanced technology available.
All right, I appreciate that. Wonderful discussion, everybody. I really appreciate all your thoughts. It's a very complex surface here. Cyber, what is security, what is trust? I think are really interesting questions that we're all really getting into. But we'll leave it there. Thank you to the audience for putting up with me taking over 14 more minutes of your time. And I'll end this. I'll pass it over to Melissa, and she'll lead us out into the breakout rooms.
So thanks, Tom. Great panel, you guys. I was really hoping to see sort of a dust up between the two different camps on how effective beamforming was at resiliency and protection. I'm hoping, Andy, I would love to hear your comments on that in your breakout panel. But for now, we will all go out to the breakout panels for one-on-one interaction and our ORAN speaker. Remember, you can use the ISART app, or there's also links in the confirmation email that you received. And we'll see you guys over in the breakout rooms.